Hello, everybody. Welcome. Welcome to lecture number 12. This is a pre-recorded lecture for our class. And so we will continue where we left off from the previous lecture. And just to jog your memory, the previous lecture, we were doing factorizations of trinomials. We started off by finishing up factor by grouping method. That's why we have this Roman numeral number 2. The first one, of course, is factoring by using the GCF. So you have factor by GCF and we have factor by grouping. And we headed into the world of trinomials. And we discussed how to factor trinomials of the form x squared plus bx plus c, where the leading coefficient, the coefficient in front of x squared, has a simple 1, or a number that's not seen. So if you just have x squared and then you have everything else, this is the case that we're considering. And we learned how to factor that by this AM method, where you find two numbers that multiply to that constant term, and that those factors add to the middle term here, the coefficient of the middle term. And that's what we've done. And we had several examples. And then we went to the more general case, which was ax squared plus bx plus c. And that's when the a value, or the leading coefficient of x squared, is no longer just a 1. It's a number other than 1. And so when that happens, we have this thing called the AC method, which is a bit more involved than the previous example form that we just discussed, where a is equal to 1. So when a doesn't equal 1, we have to do a few more steps beforehand. We have to multiply the a value with the c value, and then we have to apply that whole idea of finding the factors of that product, and then finding what factors add to the middle coefficient. And when we do find it, we split up the middle coefficient, and then now we have 4 terms, and these 4 terms are grouped into 2 groups. And then we finish off this factorization by applying the factor by grouping technique, and voila, we get our factorization at the end. So that's what we have been discussing factoring pretty intensely, and we're just going to continue on. But now we're going to be headed into this realm of what they call, at least in your book, they call it special factorizations. So all of these factorizations that we do today are under the umbrella of special factorizations. And just by going off of the enumeration that we've done with the number of the different techniques for factorization, number 3, we left off on factoring trinomials. So the 4th technique, factorization technique, that we're going to continue to study is the difference of perfect squares. So that's what we're going to be discussing. If you recall, when we talked about multiplying special products of polynomial expressions, we talked about multiplying the sum of 2 terms with the difference of 2 terms. And I made a note that we were going to come back to that. And in the factorization perspective of that special product, it's known as the difference of perfect squares. So these special factorizations have a certain result, or a certain form of the result, that we should already expect. That's why they're special. So what is that result? Well, when we have 2 squares, right, when we talk about perfect squares, we're talking about expressions that that are a result of taking a number and that number being squared, or not necessarily taking a number, you can take a variable and squaring it. So the moment you have a variable and you square it, this whole thing, a squared, is a perfect square. And so when we have a squared and we subtract it by some other perfect square, we have a factorization for it. We have a minus b multiplied by a plus b. This is probably one of the most well-recognized factorization forms or techniques. So we're going to be seeing how we can identify expressions that are different to perfect squares, and then from there we're able to factor it into a product of two binomials. And if you notice, one of those binomials, right, has a minus sign and the other one has a plus sign. And of course I can interchange the plus being here and the minus being here. The order of operations of multiplication, because it's commutative, that does not really matter. And if you see, you can prove it to yourself that if I were to distribute everything and by foiling, correct, by multiplying it out, I do indeed get exactly what's on the left side, because the a times a becomes a squared, a times b is ab, negative b times a is negative ab, and negative b times b is negative b squared. So those middle terms cancel out and you're left with a squared minus b squared. So that does work. I just want to briefly talk about perfect squares. So the perfect squares, these are numbers that you should already have in your head and be able to identify them. So we can start from the smallest, right? Obviously 0 squared is 0. So 0 is a perfect square, believe it or not. And then when you take 1 and we square it, 1 is also a perfect square. So I should say numbers enclosed by the pink boxes, by a pink box below, by a pink box below represent a perfect square. So I'm just letting you guys know that this is a perfect square. And so 0 is a perfect square, 1 is a perfect square, 2 is not a perfect square, but when we square 2, we do get a perfect square, and that's 4. And we can just continue on this list. 3 squared, we get 9. I know many of you might be familiar with these numbers here. 4 squared, 16. 5 squared, 25. 6 squared, 36. 7 squared, 49. 8 squared, 64. 9 squared, 81. 10 squared, 100. 11 squared, 121. 12 squared, 144. So these are the ones that you may have most likely have seen before. But of course, I'm just emphasizing the importance to know these numbers by heart, be able to see them and know exactly, oh, I know exactly what squared gets me that number. So if I see 121, I know exactly that's 11 squared. But I'm just going to include a few more. So 113 squared is 169. 14 squared is 196. 15 squared is 225. 16 squared is 256. 17 squared is 324. Pardon me. No. Pardon me. 17 squared is 289. 18 squared is 324. 19 squared is 361. 20 squared is 400. And of course, this whole thing keeps going, but it's good to know at least the first 20 perfect squares or even 25, just to have an idea of how these numbers look like as you go up the list of numbers that we have that we're able to square. So now we see all these numbers that are enclosed in a perfect square, in a enclosed in perfect square, in a pink square. And these numbers, we should always be able to see, okay, I know exactly what number squared gives me that number. And this will prove very helpful, especially when we have to factor difference of perfect squares. So let's see an example in action. And of course, we'll make our way to more complex ones, but we will slowly get there. Let's see, perfect. Yeah, factoring perfect square. So if I get something like this as an example, x squared minus 16. So I have x squared and then 16. What do I notice? 16 I know is a perfect square, and I can rewrite this as x squared minus 4 squared. Do you see this? And now, do you see how this is reminiscent of what I have here? I know that if I have something squared minus another thing squared, I can rewrite this as a difference of those two terms multiplied by the sum of those two terms. And this is exactly what I have. I got something, which is x squared, and I got another thing, which is 4 squared. So then the factorization becomes x minus 4, x plus 4, and I have factored the difference of perfect squares. So eventually you start to get, as you do them more consistently on a more consistent basis, you start to get a feel for what to do based upon what kind of expression you have to factor. So I'll give you another one. What if I get 25 x squared minus 81? So here you have to be a bit more careful. What do we recognize? 25, and we recognize 81. They're also perfect squares, correct? So then I can eventually, this step here is like an intermediate step, right? So I'm just going to write this this is like an intermediate step, because this gives us the a squared minus b squared form. Eventually, you won't have to do that, or you won't feel the need to do that. But for now, I'm just going to do that to make sure everyone's on the same page. So I'm going to rewrite 25. I'm going to write it in pink. I'm going to write it as 5 squared. That's what 25 is. It's 5 squared. And I'm going to, instead of writing 81, I'm going to write 9 squared. And then I'm going to show you that this is 5 squared. This is x squared. So I can rewrite 5 squared x squared as 5x parentheses squared minus 9 squared. Okay, so remember there's a rule here. Just recall one of the rules of exponents, or a law of exponent. One of those laws is that if you have a base, a product of two bases, right, raised to the same exponent, I can rewrite this as one of the bases to that exponent multiplied by the other base times the exponent. So that's all I'm using here. That's why I can say, oh, this is like a separate base and this is a separate base, but they're multiplying one another because they're next to one another, and they both have the same exponent. So therefore, I can write that as a group. 5x, I'm squaring that, and I'm subtracting that by 9 squared. And so by the difference of perfect squares, I know exactly that this will result as 5x minus 9 multiplied by 5x plus 9. And so I have also factored the difference of two squares, such as this, because I'm able to recognize 25 and 81, they're perfect squares, and so I can rewrite them as the number squared. And then from there, I have the form a squared minus b squared, which is right here, a squared minus b squared. And so then I can use the factorization of difference of perfect squares. So eventually you start to see this is kind of a bit repetitive, and at the same time, it's going to become more intuitive. You become more familiar with this idea of difference of perfect squares. So let's see, what if we have something that looks a little bit more strange, such as this, 1 minus 9a squared? What if I have something like this? Again, for now, all these examples will be difference of perfect squares, so it's nothing out of the ordinary. But I recognize that 1 is really what? I can rewrite this as 1 squared. And I recognize that 9 is really what? 9 is 3 squared. So I got 3 squared a squared, which means I can write this as 1 squared minus 3a parentheses squared. Now this is the difference of perfect squares. I got something squared minus another thing squared. I got 1 squared minus parentheses 3a squared. So by the difference of perfect squares, factorization, I can now write this as 1 minus 3a multiplied by 1 plus 3a. So here are our examples: x squared minus 16, that's factored as x minus 4, x plus 4, 25x squared minus 81, that's factored into 5x minus 9 times 5x plus 9, and 1 minus 9a squared is factored into 1 minus 3a times 1 plus 3a. Okay, and so I'll give you a few more. Because this stuff can get kind of tricky, actually, as you get into a bit more complex expressions. So what happens when I get something like this? 64 minus x squared y squared. What's 64 minus x squared y squared? So now you're like, wait a minute, why do I have two of these terms here tagged up with different bases? The important thing is that the exponents are both 2's, and that 64 is a perfect square. So I can rewrite this as 8 squared minus parentheses xy squared. So I got 8 squared minus parentheses xy squared. So I have the form of the difference of two squares. So now I can write this as 8 minus xy times 8 plus xy. And now I have the factorization. I did it. Even though maybe it's not something you see every day, the xy, but that's the factorization of this particular difference of two squares. So again, I'm just rewriting them in such a way that I can employ or implement the difference of perfect squares form or factorization. I hope that that's clear. I do want to give you a few more examples that are a bit more on the advanced side. So I'll just give you like two of these. Nothing too crazy. So what if I get something like this? 25 x squared y to the fourth minus 121. So the x squared y to the fourth might be something that's glaringly different. It's similar to this, but as you can tell, now the exponents are not necessarily twos. One of them is two, the other one is four. But the good thing is, at least we understand that these are perfect squares. So why don't we rewrite that as perfect squares? So 5 squared, x squared, y to the fourth minus 11 squared. So again, I want to rewrite this expression as something in parentheses squared minus the other thing here, which is 11 squared. So far, that's what I have. And so far, I have these 2's here. But the problem you may see is, hey, this 4 is not part of this difference of perfect squares. We're not talking about raising anything to the fourth power. We're talking about raising things to the second power. So then the question becomes, how can I rewrite y to the fourth as a power of 2? No, as an expression, I should say more explicitly, as an expression with 2 as the exponent. So if you notice, y to the fourth, I can also rewrite this as y squared squared. Isn't this true? When I have a exponent, such as this, raised to another exponent, what do? We multiply the exponents. So I can rewrite 4 as y to the fourth as y squared parentheses squared. So look what now this becomes. So let me rewrite this over here. I can rewrite this as 5 squared x squared. And just to emphasize, this is going to be y squared parentheses squared minus 11 squared. So the great thing now is that all of these terms are squared. Now what does this become? This becomes 5xy squared, and the whole thing's parentheses squared minus 11 squared. And now I have that a squared minus b squared form, and this becomes 5xy squared minus 11 parentheses 5xy squared plus 11. So this one here was a bit more involved because there's several terms actually. For the first term to consider, you got 25x squared, and now this y squared, y to the fourth business, where we want to rewrite it with 2 as an exponent. And so this is my result. So if you understand that, then you're gonna understand the more complicated ones are similar to this. Okay, so this will be the last one of this kind. What if I have, for example, 100 m squared n to the fourth minus 169 y to the sixth. So now we start to see, okay, now you're just making these a little bit bigger than they should normally be. But the important thing is that they're even, which means if you have a number that's even, it means that 2 is a factor of that number. So you can divide those numbers by 2, which is exactly what we're going to implement here. What do we notice? We notice that the coefficient 100 and 169 are perfect squares, perfect square numbers. So I can rewrite 100 as 10 squared. I have m squared, and we just discussed this whole y to the fourth, and in this case I have n to the fourth, so I can rewrite the n to the fourth as n squared squared. 169, I can rewrite that as 13 squared. Now y to the sixth power, 6 is an even number, and I can and the point here is similar to what we just did with the y to the fourth in the previous example. I want to rewrite y to the fourth as a exponent, as an expression with an exponent of 2. In this case, I have y to the sixth. So I want to rewrite y to the sixth. So rewrite y to the sixth with the same goal in mind that I had here, right? Rewrite the expression with 2 as the exponent. So in order to do that, I need to rewrite y to the sixth as y cubed, parentheses, squared. Because, why is this? 3 times 2 is 6. So I can rewrite now y to the sixth as y cubed, and I'm going to rewrite this as this number here, y cubed. This whole thing is squared. So now I can rewrite it as the following. I got 10m n squared, parentheses, raised to the second power, minus 13y to the third, parentheses, to the second power. So now what do I have? I got two terms with certain bases that kind of long, but the whole point is that both of these bases have 2 in the exponents. And so therefore now I have this form, a squared minus b squared, which can be rewritten as a minus b times a plus b. And so I'll do so here. This is going to look like 10mn squared minus 13y cubed, parentheses, multiplied by 10mn squared plus 13y cubed, parentheses. And so therefore, I have factored this difference of perfect squares. So we've dealt with 6 examples that implement this idea of difference of perfect squares. And I hope you see why it's important to go through all of these perfect square numbers so that the difference of perfect squares factorization proceeds very almost easily as we look at these expressions. Okay, so that's one of those special factorizations, difference of perfect squares. So now that we've touched upon that, let's look at the next one. So this is going to be number 5. And this is going to touch upon one of those special products that we discussed earlier in the earlier lectures, a few lectures ago. And this is called the not the difference, but perfect square trinomials. This is a pretty interesting one. So we talked about trinomials, right? But they're a special kind of trinomials called perfect square trinomials. So it's kind of it kind of piggybacks off of what we just done with difference of perfect squares. But the only difference here is that now we're dealing with trinomials. If you see in the previous one, we're dealing with just 2 terms, so binomials. So recall, this is you're required to recall special products, as they call them. So special products, if you remember, we talked about what happens when you square a binomial, correct? So when we square a binomial, and what I mean by that is I take either a binomial that looks like 2 terms and you're adding them and you're squaring them. What do you get? You get a squared plus 2ab plus b squared, right? And then we can have the other version, which is when you have a binomial and you're subtracting the terms together, but you're squaring it nonetheless. And you get a squared minus 2ab plus b squared. And these formulas don't just come out of the sky. You can actually find what this expression would be when you expand a minus b squared and you multiply a minus b and you multiply it to itself. And when you do so, you see that the terms in the middle are not canceled out. In this case, as it is in the difference of perfect squares, but they actually they have a middle term called a negative 2ab. And the same thing goes for a plus b parentheses squared. Now, that's what we talked about. The square of a binomial produces a trinomial, but the important thing now is that we're going to be going in the opposite direction. We're going to be looking at perfect square trinomials and going into the direction of finding the factorization of it. So that's what we're going to be interested in. So this is the square of a binomial. You know what? Maybe I should make this a different color. So this here on the right, this is called a perfect square trinomial. So let's see. Let's start out with a different. Let's start out with an example where we're going to factor this expression in two ways. We're going to do it the way that we would normally do it, and then we'll do it the way with perfect square trinomial. And hopefully you appreciate why we consider this perfect square trinomial factorization as something that's a special kind of factorization. So this is a trinomial, right? As we have seen before, this is the case where the a value, in this case, 16 is a number in front of x squared that's bigger than 1. So what would we normally do? Wouldn't we normally multiply 16 and 25, right? This is the AC method. So by AC method, what do we do? By AC method, we multiply 16 and 25. And when you do so, you get 400. And then we want to find two factors that multiply to 400, but when you add them up, give you negative 40. So you should see this is quite simple. If you multiply negative 20 with negative 20, you get positive 40. So that checks out, that example. And then if you do negative 20 plus negative 20, you get negative 40, which is also another plus, right? That's the middle term. And so we figured out those two numbers, negative 20 and negative 20. I can rewrite the middle term, 16x squared, and then I'll do this, minus 20x, minus 20x. This is plus 25. This is part of the AC method for factoring trinomials that we've seen before. Let me see if I change this. This might be a little bit better. And so now I can group them. And when I group them, I can factor from the first group. I can factor a 4x. This becomes 4x minus 5. From the second group, I see I have a negative here in front. And if you don't take out this negative, then I won't have an expression here that's the same as 4x minus 5. But if I do take out the negative, that's exactly what I get inside. I take out a negative, in this case, not a 4, but a 5. And when I do that, I get 4x minus 5 when I factor out that negative 5. And do you see 4x minus 5 and 4x minus 5 are both the same. And then when I continue with factor by grouping, I get 4x minus 5 as I factor that out. But what's left is 4x minus 5 again. So I got 4x minus 5 times 4x minus 5. That becomes 4x minus 5 parentheses squared. What did we just factor our trinomial into? We factored it into a square of a binomial. And because the factorization is a square, so it's something squared, then we don't just say that this is a trinomial. We actually say this is a perfect square trinomial. Why is it a perfect square? Because we were able to factor the trinomial as a binomial squared. So therefore, this is a perfect square trinomial. Now, you may see the problem with this if you realize that these numbers here, they can get quite big when you multiply them. And maybe finding those numbers, this was a relatively simple one, but there might be numbers that are a bit bigger, and when you multiply it, it's a much bigger number. And finding factors for that number that add to the middle coefficient, it could become much more taxing. However, if you recognize this is a perfect square trinomial and you know the perfect square trinomial form, then it becomes almost a cinch as to how to factor. So I'm gonna look at this now from the perspective of recognizing that it is indeed a perfect square trinomial. Now, in order to do that, though, I need to go back and study this form a bit more. And the reason why I'm going to use this form instead of this form, because this example has a minus in the middle term, so I'm going to use the minus term here. So, so to have it as formally, the perfect square trinomial factorization is if I have a trinomial that has this form, a minus 2ab plus b squared, the result of factoring this trinomial gives me a minus b parentheses squared. Now let's try to see how we can mirror this with the example that we have. 16x squared minus 40x plus 25. Do you see how we pair up these terms together? How we can group, in a way, these terms? And what I mean by that is, look what I can do. I recognize, look at this term here and look at the last terms. The last two terms are perfect squares. So I'm going to write conditions, or I should say, I should be a bit more strict with this. These are requirements for a perfect square trinomial. There are two of them. The first one is that the first and last term are both perfect squares. That's the first checkpoint. That's the first requirement that must be met. 16x squared is a perfect square. Check. 25 is a perfect square. Check. Why are they perfect squares? Well, I can write this as 5 squared, and I can write 16x squared as 4x parentheses squared. So both of these terms here coincide with this idea of a squared, 4x squared, b squared, 5 squared. That's 25. Do you see? Now the second requirement, it's a bit strange to write this, but the second requirement is the following. The second requirement deals with the square roots of the first and last terms. And if you take the square roots of the first and last terms and you multiply them together and double it, that should be the middle term. So I'm going to say this. The middle term must be twice the product of the square roots of the first and last terms of the trinomial. So number 2 is a little bit strange to think about. It's not as apparent as the first first requirement. The first requirement, you can just glance at the first and third last term and recognize, hey, those are perfect squares. But the middle term, how do you know that's double the product of the square roots of the first and third? So again, this is just to take things slow, and then eventually this will move quickly. What is the square root of the first term? Square root of first term. I already have it kind of written down, but it's not written as a square root. Square root of first term. Well, if I take the square root of 16x squared, I get 4x, right? Because 4x, when I square it, is 16x squared. So 4x is the square of my first term. And I'm going to call this the a value, right? This is my a. Then the square root of last term. Well, the last term here is 25, and the square root of 25 is 5. So I'm going to call this my b value, right? So I got my a value and I got my b value. Now that middle term, what do we say? That middle term here, 40 or negative 40, has to be what? 40 has to be twice the product of a and b. So you have to check. So check. If I do 2ab, what do I get? I get 2 multiplied by 4x multiplied by 5. Is this, the question is this 40x? Well, 2x times 4, 2 times 4 is 8 times 5 is 40. So this is 40x. Yes, this is true. So this trinomial, this example that we had originally, is a perfect square trinomial because the first and last terms are perfect squares, and that middle number is twice or double the product of the square roots of the first and last terms. So look what I have. And if I write this a bit here, a bit the way I wrote it, 4x 5, right? Plus 5 squared. If you notice, look what I have. I got a squared. I got a here minus 2ab plus b squared. I have this. I can rewrite this as this form, a squared minus 2ab plus b squared. So let me just write that again. So 16x squared minus 40x plus 25. I can rewrite this as 4x parentheses squared minus 2 times 4x times 5 plus 5 squared. This is a perfect square trinomial. I know what the perfect square trinomial formula is. If I have a squared minus 2ab plus b squared, all I have to do is put parentheses, take the a, subtract it with the b value, and make sure you have a 2 as your exponent. And that's it. I already know what my a value is. A is 4x. 5 is b. So then the factorization will be 4x minus 5 parentheses squared. And that's it. You may say, but hey, it looks like we did a lot more work, or maybe just the same amount. Yeah, it looks like it's a lot more. Again, this is more of a background and more of a drawn out explanation, but knowing perfect square trinomial factorizations will save you time from having to do AC method, because eventually it will just be these steps. It's just going to be a 2-step problem once you have the understanding of what perfect square trinomial is. So let's see more of these in action. So for example, I got 49x squared plus 28x plus 4. So for these, you may be tempted to say that, oh, now the problem with showing this is that a lot of students start to think that every trinomial is perfect square. Not every trinomial is a perfect square, only some. But let's just make sure that it is. So check. You always want to check first. Check first if trinomial is a perfect square trinomial or not. So it's like a checklist. The first step, are both the first term and the last terms, are they perfect squares? So is it a perfect square? Well, obviously 49 is 7 squared. So the square root of 49 x squared becomes 7x, right? X squared, the square root of x squared is x. The square root of 49 is 7. So the square root of 49x squared is 7x. And the square root of 4, it's 2. So yes, check, check. And now, and we call this what again? We call 7x my a value because it's the first term, and my 2 becomes my b value. So these work out. The second thing is I have to recognize, hey, what happens in the middle? Is 28x, is this equal to 2 times ab? Which means that if I multiply 2 and with a and b, which is 7x, and 2, do I get 28x? Well, 2 times 7 is 14, times 2 is 28. And I do indeed have a middle term who is double the product of the square roots of the first and third, or first and last terms. So again, and then now this becomes a two-step process, if even need be. Eventually, it might just be a one-step process. But 49x squared, I can write this as 7x parentheses squared. The 28 can be written as 2 times 7x times 2, and this 4 becomes 2 squared. This has the form what? A squared plus 2ab plus b squared. We already know what 2a squared plus b squared. You see here, we already know what 2a squared plus 2ab plus b squared. It becomes a plus b squared. So again, when you have a plus here, if you notice, the only difference between these two perfect square trinomial forms is that the second term has a plus or minus. If they all have pluses, and if the middle term has a plus, the square of a binomial is a plus. If it has a minus instead, then this minus is going to be present. So in this case, they're all pluses, so I'm going to have the form ax, a plus b parentheses squared. So in this case, would be 7x plus 4 parentheses squared. Again, this is a plus b squared, which is tied with this. And so this will be my final factorization. And that's how we go about factoring perfect square trinomials. So of course, I'm going to give you a bit more, not so challenging, but just a bit, trinomials that have a different feel or different look. So for example, if I have 4a squared minus 36ab plus 81b squared. So again, is this a perfect square trinomial? Check. We'll have to check the 4a squared. I can rewrite this as 2a parentheses squared. So that works out. 81b squared, I can write that as 9b parentheses squared. So far I have my a, quote unquote, well, even though a repeats, and I have my b value. Is the middle term, is 36ab, is this equal to 2 times 2a times 9b? Well, 2 times 2 is 4, times 9 is 36. So 2, 2, and 9, when you multiply them, it gives you 36, and AB do become AB when you multiply them. So the middle term also works. So this also becomes minus 2 times 2a times b. And now this has the form a squared minus 2ab plus b squared, which results in what? The factorization. And the only thing that happens is that at the first term, when they take the square root of it, that stays 2a, and the last term, which is 9 in this case, and this should be a minus because the middle term here has a minus sign. So that's how we get this factorization. Okay. Okay. Let's see if I have one more of those. Just give you one more, and then we'll go on to the next kind. So I'm missing. Yeah, I think I'm missing one. Thought I had one extra one, but I think we can move on. It's missing here. Okay, yeah, we can move on from here. So this is a difference of, so we've done difference of perfect squares, and now we've done factoring perfect square trinomials. Okay, so we've dealt with this the difference of two squares and perfect square trinomials. And now that was the what? That was the fifth one, if I'm not mistaken. And now the sixth one, the sixth kind of factorization, a scenario or case, is when you have what are called sum or difference of perfect cubes. So one thing I should have mentioned about perfect squares and the difference of perfect squares is that the difference of perfect squares are factorable, and they have, you can factor them, so you have this form a squared minus b squared times a minus b, a plus b. But one thing I just want to note, for example, just want to note that there are many expressions that are not factorable. For example, a squared plus 4 is not factorable. It's not factorable. You can't multiply two of anything that when you multiply them give me x squared plus 4. So the sum of perfect squares is not factorable. The sum of perfect squares of, I should say, two perfect squares is not factorable. But the difference is, and to be a bit technical, it's not factorable. I'm just going to write this in parentheses over the reals, or I should say the real numbers. When we talk about complex numbers, actually, this is factorable. But in this course, in the scope of this course, we're only dealing with real numbers. So because we're only dealing with real numbers, this kind of expression cannot be factored. But if we have x squared minus 4 instead, then of course we have the difference of two squares. And the reason why I brought this up is that in this case, when we have perfect cubes, actually the sum and difference are possible, are factorable. They are. But before we continue, we should talk about what are perfect cubes. The same way we've talked about perfect squares, what are perfect cubes? What are the examples of perfect cubes? So we'll see here that 0 squared, for example, sorry, 0 cubed, right? 0 to the third power is 0. 1 cubed is 1. So 1 and 0 are both perfect squares and perfect cubes. Of course, 0 is just, it's not that special of a number, at least not for this. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. 6 cubed is 216. 7 cubed is, I think it's, hold on. I'm pretty sure. Yeah, it is 343. That's what I thought. 343, 8 squared, 8 cubed is 512. 9 cubed is 729. 10 cubed is 1,000. So again, the numbers that are enclosed by a pink rectangle box here, these are called perfect cubes. These are numbers that when you take a number and cube it, you get that number. That's what that perfect cube is. So now when you see 1, you see 216, pardon me, you see 512, all these numbers, you should be able to recognize and identify them as perfect cubes, and you should be able to say, okay, this number cube gives me the perfect cube that I'm looking at. Okay? Now, I'm going to give you the formula for this, and the formula for the sum of perfect cubes the following: a cubed plus b cubed. So hence we have perfect cubes, sum of them. This will equal a plus b, parentheses, a squared minus ab plus b squared. Okay, this is the difference. This is the sum of two perfect cubes. This is what the sum of two perfect cubes is factored into. And then the sum of perfect, sorry, not the sum, pardon me, I just wrote that. The difference of perfect cubes. This is a cubed minus b cubed. This results in a minus b, parentheses, a squared plus ab plus b squared. So you start to realize, wait a minute, they look very similar. The only difference is the signs, right? If you notice, plus, plus, minus, plus, but the rest of the terms are identical. And this is minus, minus, plus, plus. So there's a little acronym people use called SOAP. So it's S, this is a little acronym. I'm sure what it uses. So, and this is an acronym used to help you remember the formula a bit. It's SOAP, S-O-A-P. Now, what does the S stand for? It stands for the same sign. So this is the same. This is the same. They're saying if this is a plus, this will be a plus. If this is a minus, this will be a minus. That's the same. Then what does the O represent? The O represents the opposite. What does that mean? That means that the plus sign, in this case, is the opposite of the negative sign. And the same thing goes for this guy, right? The minus sign here is the opposite of the plus that we started with. And then we have the last two letters here kind of go together. So I'm going to bunch them here together. Always, A stands for always, and P stands for positive. So what does that mean? That means that the last term, if you notice, is always positive. So that's the acronym, SOAP. Same sign, opposite, always positive. And that's one way to help, for some, help them remember that this formula. Again, the sum and difference of two perfect cubes, they have similar terms, I should say the same terms. It's just that the signs are flipped around. In particular, these are exchanged, interchanged. Okay, so now let's put our formula to the test with real life examples. So now that I have a difference, right? Let's see what happens when I have something like this. 8x cubed minus 1. I want to factor this expression. I should notice that 1 is a perfect cube because 1 cubed is 1, and 8 is a perfect cube because 2 cubed is 1. So I can rewrite this as 2x parentheses. All right, let me slow down a bit. This is 2 cubed x cubed minus 1 cubed. And then this here, 2 cubed x cubed can be rewritten as 2x parentheses cubed minus 1 cubed. This could be considered my A. This can be considered my B. This is A cubed minus B cubed, which is exactly what I have here. And now what happens, I'm going to use this form or factorization. So this is going to become what? This is parentheses 2x minus 3, parentheses 2x squared plus 2x times 3, that's AB, plus 3 squared. So again, all I did was I utilized AB, A, this is A, this is B, this is B squared. So all I did was I'm replacing all the A's with the proper A's and the B's with the proper B's that I have. And so when I do that, 2x, when I square it, that gives me 4x squared. 2x plus times 3 becomes 6x. And then 3 squared becomes 9. And I'm just left with the 2x minus 3 to the left of it. And this is my final factorization. And this is it. Okay. This is it. So this is a difference of two perfect cubes. Next example. Next example is I will give you a sum. So what if I get something like this? 64x cubed plus 27y cubed. Recognize 64, perfect cube, 27, perfect cube. I can rewrite this as 4 cubed x cubed plus 27 is 3 cubed y cubed. This equals 4x parentheses cubed plus 3y parentheses cubed. This is A, this is B. So now this becomes what? 4x plus 3y, AB, right? Then this becomes times 4x parentheses squared minus 4x times 3y plus 3y squared. And let me move this a bit more to the left. Again, what am I using? I'm just using the difference of the sum of two perfect cubes. That's it. I got a plus b, a squared minus ab plus b squared. That's exactly what I recognize. Like this is a, this is b. So this is a squared minus ab plus b squared. So let me make sure I got this. This is a sum of perfect cubes. So then what do I have? I got 4x plus 3y. And then 4x parentheses, when you square it, you get 16x squared. 4x times 3y is minus 12xy. And 3y squared becomes 9y squared. And boom, we have factored a sum of two perfect cubes. And all we did was utilize our formula that's been given. So what do we need to know? Of course, we need to know what numbers are perfect cubes, so we should be able to see it as immediately as possible. Okay, and in the time remaining, I will look at the last, a special factorization, and these are more of the special ones, the sum of difference of perfect cubes, and the difference of perfect squares and the perfect square trinomials. Those are the main ones. And the reason why I'm not saying that this is a completely special one, but it is. It's related to a factorization that we've done already, and that's when we have polynomials or trinomials in quadratic form. Trinomials in quadratic form. Now, what is that? What does that mean? I'll give you an example. For example, if I have b to the fourth minus 13b squared minus 90. Okay, this is an example, and I'll give you another example, and we'll be finished with this. This almost looks quadratic. The only issue is that the 2 is not the highest exponent, it's a 4 instead. And what I mean by quadratic form is the following. This is something that you've never seen before. So this might be this little step that I do here. You may have not seen before. It may seem insignificant, but it helps a lot. I'm gonna do the following. I'm gonna let u equal b squared. This is known as a substitution step. So I'm going to say b squared, I'm going to call that u. So that means that b squared here, I'm going to call it u. But what happens when I square u? U squared. That means I have to square b squared, right? Because that's what u is. But when I square it, don't I get b to the fourth? So b to the fourth actually is u squared. Now look what I get when I do such a substitution. I get something in as a quadratic, don't I? Do you guys see that? So do you see how I went from b to the fourth minus 13b squared minus 90? And now I went to u squared minus 13u minus 90. This is a quadratic. Now, forget just for a moment about this and look at this. How do we factor this? Well, we've done it already. We find two numbers that add, sorry, that multiply to 90 and that add to negative 13. And there's many factors for 90, and one of those factors is 18 and 5. So 18 times 5 gives me 90. Because it's negative, the product, one of them must be negative, and the term in the middle is a negative, so one of the numbers has to be bigger than the other. Or I should say more negative than the other. So then the factorization becomes this, look. So this has to be u. This has to be u, the first two terms. Negative 90, well, negative 90, again, 18 and 5 will be the more likely candidates. Negative 13 comes from the fact that negative 18 is added by positive 5. So we have here negative 18 and positive 5. So what did I just accomplish? I accomplished that factoring u squared minus 13u minus 90. That factors into u minus 18, u plus 5. But where did this u just pop up out of nowhere? U was used to replace b squared. But I really care about the original, right? That's really what I started with. This was just like a little like an almost like you can say like an artificial step, so that we recognize that this has a quadratic nature to it, but not quite. If I were to make this substitution as I did, then I do have a quadratic, but I have the quadratic only with respect to the variable u, not with respect to b, which is what I originally have. So all I have to do now is replace back what u was. And what was u? U was b squared. And this is what I mean by factor by a quadratic form. So it looks kind of strange, maybe, for the first time, but that's what it is. We recognize that this term here, originally this trinomial, is a quadratic in nature. If I were to make this substitution, which it is, factor that, and then replace back the u for the original. So that's the first kind. And the second kind is this one here. Something that has something like this. X plus 3 rad x plus 2. This is also a quadratic in form. Now, the u substitution will be a little bit different for this. I'm going to say let u equal square root of x instead. So as you start to see, the u substitution occurs by replacing the middle term. I replaced the middle term with u. And then you realize, but why do I do that? Because if I square u, what happened? I square the square root of x in this case. But if I square the square root of x, I'm left with x, which is exactly the beginning, the first term. So I can now replace x with u squared. I'm going to rewrite that with a blue u. So now the first term is u squared, and this becomes plus 3 times u plus 2. Do you see that? So the first term that we have, the first trinomial that we have, had square root of x and x in it. But because it's square root and x, it's really squaring one to get the other. So I can rewrite that now as using a new variable. And look what I have. I get a quadratic, don't I? And this quadratic can be factored. U squared plus 3u plus 2. We'll multiply to 2, it adds to 3. It's 2 and 1. So I get u plus 1, and I get u plus 2. Okay? But of course, I don't want to stay with the u variable. I refer back to what the u represented, and it represented rad x. So I'm going to replace rad x with the u, and that has been my final answer. So we've covered quite a number of special factorizations. We started with the difference of perfect squares. We went to perfect square trinomials. Then we went to sum and difference of perfect cubes. And lastly, we talked about rewriting trinomials that are in quadratic form. So if you have something that starts with the b to the something to the fourth power, and then something to the second power, then that's a quadratic in form. And then if you have starting something with just a single variable and the middle term is the square root of that variable, that also has a quadratic nature to it, and we can factor it. Okay, so that is what we covered today.